All right, everybody. I'm going to go ahead and kick off the meeting. So, thanks everybody who's joined in today. It's always a lot of fun. A lot of fun these discussions for me. I learn a lot. Anyhow, today the agenda is light at the moment. So, Osama, I believe, will take some Q&A on RATLS. And if nobody else has something that they wanted to chat about, I was going to suggest that we take a look at the current set of uh, tracks and topics that we've been talking about historically and some of the upcoming discussions we hope to have and do a bit of brainstorming, see if there's any other ideas people want to throw in there. And anyway, that's what's on the agenda for today. I'm going to put a link into the chat window if you can go ahead and make sure you put your name and on the meeting notes so we know who's joined in for the meeting today, if you can or want to. And with that said, Osama, are you ready to take your Q&A for the RATLS stuff you were talking about last time?
Yeah, sure. So yeah, I'm ready. I can
Okay, thank you.
if someone has any question or some specific part which I was maybe rushing around, so we can have a look at that.
Yeah, perhaps you want to blast through a few slides or something just to refresh our memory and let us page back in what exactly we were thinking last time.
Sure. Yeah, I can do that. If there are no specific questions, then we can slowly recap a little bit. Yeah, so this was about the TLS and remote attestation combination. And I kind of gave an idea that we had recently worked with, that is, the TLS provides good protection only if the key itself is protected. And intrinsically, it has no protection for the key, which I described as one of the problems. And the idea was to combine remote attestation to see if it can help. And there we had, for attested TLS, three main, let's say, kind of visualizing how it can be combined, which I will slowly go ahead with just an overall idea that pre-handshake attestation, post after the handshake, and intra, which is in between the handshake. And the important point here was the evidence generation, which is classifying the three approaches, and all the three are used in confidential computing. Any questions? Okay, then I will go ahead. So, and then I described a few bits and pieces of the formalization that we did, and we did some additional testing on that. I will just quickly recap what we had. TLS protocol, in its intrinsically, the security actually depends on the privacy of this key, and this is quite symmetric, which means that we have taken server as a tester in the scenario, and it can be the other way around. So it's only shifting this certificate to the client, which is the default that the server presents the certificate. So we have done only server as an attester for specifically for this case. And this is the standard TLS 1.3 RFC 8446, I think. And as I said, intrinsically, it has no validation of security state of endpoint, software, and platform, meaning that if this key, the whole security argument is based on the confidentiality of this key, and we have the client or the other endpoint does not have specifically any guarantees on this. And this is where remote attestation can actually help. And it has been exploited a lot. 15 major CVs on the exploitation of TLS. And that was the motivation to see how remote attestation can actually help, or if it actually does help. So remote attestation, as you all know, it's at a very high level, like verifier sending a attestation request, evidence generation at attester, and then sent over. and then it can make a decision whether to trust this and send over some secrets or sensitive data. Unless someone has question, feel free to interrupt me. I will quickly try to, maybe in 5 minutes, just recap all what we did. And then the project that we would just conclude is that authentication is by default not provided by the TE mechanisms, and that's where comes the idea to combine the two things together to see if they can fulfill this authentication part. And to date, there is no standard way of implementation of remote attestation. So there are problems in TLS, which I described. The priv LTK, the private part of the long-term key, by default has no protection guarantees. And there are problems in remote attestation, namely these two. And the idea then was to see how to combine the two protocols and analyze them formally. And this is just describing the two things separately, and the three ways of combination of these protocols can be pre-handshake attestation. And in confidential computing domain, Intel's RATLS is one of these protocols. And the idea of this classification of the three things is basically the point of generation of the evidence, and more specifically, not the claims generation, rather the claims transmission, which is including the signatures and so on. And then we had an idea that if there is no channel binding between the two protocols, there is a possibility of the replay as well as the relay attacks. And this replay attack is what we have formalized specifically in this work. This relay attack is not yet part of the work. It can potentially be seen next in the future work. Then this post handshake, meaning that the evidence is generated after the TLS handshake. TLS handshake completes. There was one question regarding this. We don't have still some very specific details from SCOAN on this, but I think we can explore that in the future. This is also very interesting. And the drawback, in my opinion, this, again, just to clarify, this doesn't mean that it does not have any security flaws or security attacks possible. This is just showing that it has a high latency. There will be a round trip for after establishing, doing all the handshake, completing all the TLS handshake. We need an extra round trip for the transmission of the evidence. And that's why at least the problem is that it has high latency compared to other options. It could be it has some security problems as well. It's just that it's not yet formally analyzed. So that's just the reason for not mentioning any security problems here. And then the final one, which is the ITF draft, Hannes and so on, who are working on this. The idea is that the evidence will be a part of the handshake itself. That is it will be generated per handshake session. And then one will have the guarantee that this evidence is only valid for this specific session, and no other session can actually validate or verify that specific evidence. And as I said, so we believe it's potentially a sweet spot, that it would hopefully, if designed correctly and verified properly, it would hopefully overcome the limitations of both of these solutions, meaning that replay will not be possible and also relay will not be possible, because the evidence will be per session. For that specific session, it will be only usable for that specific session. And the second thing is that the latency is not required because it will be transmitted as part of the certificate message. So the thing here was that it completes the handshake and then sends over an evidence that would not be required because it's part of the certificate message itself. So no extra round trip will be required. Okay, and
so real quickly, just to make sure to land on that last one a bit, because
Sure.
What we had presented previously for what we at Google had done with the STET protocol with attestation evidence and TLS, I think, is what you're calling post-handshake attestation. And the difference that you're contrasting here is that it combines messages. So instead of having to have a separate like attestation handshake, it does it at the same time as the TLS handshake. Is that right? So it's strictly a performance improvement. Is that what you're saying?
So were you here last time, Keith? I don't recall.
I think I missed the last meeting.
All right. Because the one question I had about that one was, what does it do to the programming model? Because to me, it sounds like the first and the last, the programming model is it's underneath the APIs you're using like to establish a TLS connection. And the middle one, the post handshake, moves it into an application level responsibility. So it will like have to be replicated with, every app, would have to kind of solve this on their own. Maybe they use a third-party common library or something, but it's kind of at the app level. That was one thing I asked about, and I'm not sure. Yeah, I didn't hear any disagreement with that from what I recall. But it was, I think people were cogitating on that a bit.
Okay, yeah, I mean, I think that's true. Like the base TLS libraries won't handle it for you. You'd have to have something built on top of a TLS library that does it for you.
So yeah, so to answer your question, Keith, I think that would be mainly a performance issue. And as I was mentioning, so specifically for SCOAN, we don't have yet any formal analysis. So that's why I don't specifically write about any security problems. It's just that it has not been considered yet. It may have, it may not have. So it's just not yet formally analyzed.
Okay.
So, yeah. So the problems, at least the performance problems, at least do exist. And Greg is also right. I think, at least in my understanding, up till now, there would be some changes on top of TLS. But I saw that in SCOAN docs, it claims that there is no change to the application required. So there is something in between the two layers, which is actually somehow dealing with the two things. But I couldn't get hold of the guy who is responsible for this, Nicolaus. So I will update on this when I have a concrete answer from him.
So I have a question.
Yeah.
So if you do a post handshake attestation, but then renegotiate the TLS handshake, does that turn it into an intra handshake scenario then?
So by
at least in the post handshake approach that we do with our split trust encryption tool, we do not renegotiate the TLS.
Right, but if you did that, would it fit the intra handshake scenario, or are there some other details that would rule it out?
Would there be a reason to want to do that?
Well, I think the point that is being made is that the intra handshake one is more secure.
That's what I wanted to clarify. I don't think it is more secure than the post handshake approach. It's more secure than the pre handshake.
Okay.
Is that right?
Yeah, that's true. So from this perspective, what we are comparing is security compared to this, more secure than this, and more performant than post handshake. So this is.
I think if you were to do that, where you do the post handshake and then renegotiate, I think you get the negatives of both at that point.
So just to clarify, what does renegotiate actually mean? So is it
you just restart the handshake?
Oh, okay, yeah. Then there is going to be again at least this latency problem.
And at that point, the attestation evidence isn't bound to the TLS session secrets anymore. So you also have the replay and relay attack problem. I think you get the negatives of both if you combine them in that way.
Okay.
Yeah, I think so as well. Yeah, because there is no channel binding, and if there is no nonce, if there is a nonce, you cannot use it in the second session. And if there is no channel binding, then there will be again the same problem of these attacks. Is it kind of proposed somewhere, the solution net that about renegotiation?
And it's a capability of the handshake, and that's often used to, to do things like refresh the keys and so forth. So there's, you may want to do it anyway. And the question is, if you were doing it anyway and you had the opportunity to reattest, would you get any benefit?
Okay, right. Any other points or discussion?
So I think maybe the pre-handshake case, it's worth noting somewhere that it may not be possible to, attest, do an intra-handshake attestation, because the modules that are in question, have exited already.
What do you mean?
So it's a, if you're in a bootstrapped environment, the boot path is going to, run, boot something else, run, boot something else, and eventually you boot into something that has a TLS capability. But there's sort of no way to, now that you have that ability, there's no way to go back and say, let's reboot and do it an intra handshake or a post handshake scenario, because it's, those environments don't exist anymore. They're transient environments. So I think the RATLS approach is anticipating that kind of a architecture underneath.
I didn't quite follow. What environment did you say was transient?
The bootstrap environment is transient.
And what do you mean by the bootstrap environment?
So you're gonna take a reset, hardware reset, then you bootstrap loaders. Bootstrap loaders load something else, but eventually you get into an environment that can support a network connection. It's only at that point in time when you can then consider, intra handshake and post handshake scenarios. But I think that applies to any of these, right? Like if I'm using, attested TLS, I still have that problem. I'd assume the SCOAN stuff has that problem too.
I'm not following what the problem that you're highlighting is, I guess.
The problem is if you're developing attestation evidence from the root of trust forward, you're going to generate evidence and prepare it for consumption by a remote verifier that isn't connected yet, right? So
yeah.
So in the case of DICE, you'll protect that evidence using certificates that are dynamically generated, and then pass them along, whether it's through SPDM or a TLS session. It doesn't matter. It's all the same kind of scenario, right? But I think it applies universally for any system, right?
I think that there is the primary difference between both would be that SPDM would have some measurements while TLS will not have. So I mean that the protocol itself would also matter into this, whether it's TLS or SPDM.
Well, what properties are you talking about? This SPDM supports collecting evidence that's been previously generated, and it supports collecting evidence that is dynamically generated. And I assume that all of the TLS variants are the same way too.
So what you are saying is that the previously generated will be analogous to pre-handshake, and the other one dynamically generated will be kind of this intra-handshake.
It's either intra or post, but I think those use cases apply to all of the solutions that are parenthetically suggested here. I don't think that it's a limitation of the different solutions. It's just these are the cases that are interesting, and those three cases apply generally to all of the solutions.
Yeah, I think so. Yeah, then in that sense, so what you are saying is basically not specifically to TLS, rather to the two layers of transport and remote attestation, right?
Mm-hmm. Yeah.
Yeah. That I agree. I think that's at that level. I think so. Yeah.
I think the discussion about the pre, post, and intra is interesting, but then it's sort of combined with something like a marketing glossy that has a list of rows and columns and check boxes against, like a feature compare matrix. I just don't think the feature compare matrix is adding any value. So I think it leads you down the wrong direction. Or at least you could have this conversation without the feature compare matrix and then do that later. But I just think it's not.
So by feature comparison matrix, you mean this thing, right? Is it correct?
So I agree that the pre-handshake scenario has potential for replay and relay attacks. Yeah. I don't think that potential is exclusive to RATLS.
Yeah, that's why I write for example. So I'm not saying it's specific to this specific protocol. And what we say is that is one example, which is.
But it's also right. But it's also the case that RATLS could be deployed in a way that it's not that it's doesn't do any of the pre-handshake stuff. It only does post or intra, and then it's just as good as an example for any of the other bullets. So I'm just saying it doesn't make sense to try to overload what I see as two slides, one slide that talks about the principles and what the issues are, and another slide that tries to do a feature compare. But you need to look at like the full spectrum of possible deployments to determine kind of which, what that comparison looks like. They might all of them might check all the boxes. And so it's not an interesting feature compare.
Previous times that we've discussed attested TLS, and again, I wasn't here at the last meeting, but like months and months ago when we discussed it, RATLS was discussed in the context of like this pre-handshake approach. I don't think I wasn't aware that it could support anything like the post handshake or intra handshake. Are you saying that it can?
Sure. It's like if the way that you achieve the security goals through intra handshake is by passing a nonce over the handshake and not finishing the handshake until the nonce has been signed into attestation evidence, right? Well, you can do that with RATLS. It requires you to generate a certificate dynamically, but that's doable.
So you generate the certificate during the handshake that used the certificate? I'm not following.
You generate the certificate that signs the nonce, and then add it to your list of certificates that you return. It doesn't have to be the same certificate that's used during the handshake, but even if it is, it's not a problem. It's just, you're providing the whole handshake, you're providing the whole certificate chain.
That would be, in my opinion, that would be a major change to the Intel's RATLS. And at least the way it is specified right now, it's going to be major changes, at least within the TLS, the way you are describing the certificate. generation and putting the nonce in there, then sending it as a part of the protocol.
Right, but we're comparing, we're trying to talk about, we're not talking about specific implementations because implementations have limitation.
Mm-hmm.
We're talking about protocols and what their security properties are.
Mm-hmm.
Right? Are there some fundamental, weaknesses based on the different approaches?
Yeah.
And it's like we're not comparing implementations. We're talking about design and architecture.
Okay, so if it helps us move past it, the examples given there, if we could ignore those and just talk about the benefits of doing pre-handshake attestation, post-handshake attestation, and intra-handshake attestation, whether or not our ATLS, its spec currently allows or could be modified to allow different approaches. Maybe that could be separated into a separate discussion.
Yeah, that would be helpful.
Okay. So with that, would we be ready for Usama to move forward in his deck?
Yeah, sure. Okay, yeah, as I said, so this is one example specifically that we have taken, and it is relevant for the group here because it's used in confidential computing and is widely used: Grameen, Reds TLS, Open Enclave, Attested TLS, SGX SDK, Attested TLS. Here is the remote attestation thing for DCAP, and on the right from the Intel's white paper specification that I was just mentioning, it described TLS 1.2. So the first challenge was how to actually merge them together and to make the formal specification with TLS 1.3 rather than TLS 2. There are already discussions on TLS working group to feature freeze TLS 1.2. So we were specifically working with TLS 1.3. And then the first challenge always is that if it is informally specified, how to actually combine the two protocols together. And yeah, it's in case of Intel's RTLS, it's the self-signed certificate, and then which contains the evidence in here. And there are then other certificates like AK cert and so on, building the chain up to the Intel's root cert. And then is the formalization part divided into 3 key parts: flow showing the model. And then for each model, we need some properties. And specifically, I have written key schedule as a separate part because TLS has a lot of keys generated, and it was the interesting part where we also found some problems in the previous formalizations. Quickly scrolling through the key schedule, this is a snapshot from RFC 8446, the whole key schedule, not actually the whole, so a part actually of the key schedule, which is showing the first stages for the derived secret. And the second stage is shown here in the green, which I have added, just to be clear that the keys which are actually used are now these ones rather than the ones which are shown in that figure. So they are specified, but here and there, like in section 7.1, 4.4, and somewhere around. But so this figure completely shows starting from a pre-shared key and ending up to a pre-shared key for session assumption for a new key for the next session assumption. And yeah, so this is where, as I said, we found some issues, which was in the India's artifacts, which have been used in a number of solutions for formalization. And the first one was that the way they generate the handshake secret is actually in this figure, or maybe I can show you a bigger figure. So handshake secret, you see this figure now, right? I'm not sure if I shared the full screen or you see the figure or you see the slides.
I think we're seeing the slide. We see key schedule with second stage for
Okay,
the title.
then I will quickly just share again, just a moment. Okay, I think now it should be the right one.
And now we see your desktop.
Okay, cool, thanks. So, this I was describing basically the salt for handshake secret, which is actually this one, and the salt is here. And in this, the input should actually be 0, whereas they have taken, due to some reason, an additional hash, which was actually wrong. And this is what we have communicated them. And similar problem existed in the salt for the master secret, which means that for the derivation of this, there is a requirement of salt2 in addition to the ICAM inputs, the 2 inputs that it takes. And this input should be 0 rather than the hash of 0 as they have taken in their artifacts. So this was the first one. And another issue was this one incorrect derivation of master secret. So independent of both of the two salts, somehow due to some reason, which is again related to the master secret here, they skip this drive secret, which is somewhat unclear to us still, which is that why this actually existed in there. So we had a look at the draft 18 of the TLS, why this was added in there. It was added between draft 18 and 19. And we had a look at around these discussions. We had a look at the IDF 98 or something around that, when the discussions happened, the PR and so on, the discussions on the working group. And we couldn't find any logical reasoning for, and the paper itself does not clearly explain, the one by INRIA does not explain why they are doing this, because there are two parts in the paper, the one by symbolic via ProVerif, the other one computational via CryptoVerif. And in one of, so the CryptoVerif part, they argue that it is, this derived secret is actually required. And surprisingly, in the same paper, actually they skip it for the other, which is the symbolic part. Using ProVerif, they actually skip this. And we were trying to explore this, why this is the case, and we couldn't find anything conclusive from the paper itself. Then we went over to the TLS working group. We explained the problems. We first actually asked why this derived secret, what's the value of this, why this was added. It was not clear from all the sources, PRs and so on. And it seemed that it's coming again from the same paper, the same analysis. And we described this problem to the working group. We don't have any answers yet. It's still open question that we will be discussing at the UFMRG working group next time. So as I said, now for formal analysis, we need a formal model. And this is what we created, a simplified thing to see and to get started with analysis of this. The handshake. So since it's a pre-handshake attestation, so handshake is, this evidence is generated beforehand. And then the major changes are in this part, which is this certificate is created, which includes this evidence. And then on this, and this certificate, this self-signed certificate is sent as part of the certificate message of the TLS. And then on this side, since it is signed via this key, which is, and one major change is that now it uses an ephemeral key rather than the long-term key, which is with the trusted execution environment. And then the verification will be done because it was signed via this key. So it will be verified using this ephemeral public part of the ephemeral key, which is contained inside this certificate. And the proof of possession is also signed via the same key, and that is here verified. And the finished part remains the same. There is no change here. This is a bit more of a detail, and now combining the two words of remote attestation and the TLS parts together, I will quickly switch to a bigger version of this, which is this one. So this is the verifier here from the attestation point of view. the client and server as defined in the TLS terminology, meaning that. Any questions? Okay, then I will proceed. So the client from the perspective of TLS, meaning that the first, the endpoint that starts the TLS connection, and server, the one which is not the initiator. And here the server from attestation perspective is acting as an attester, and this one as the relying party, and this is the verifier. And the thing which is not shown here is also like specifically for Intel or in general terminology, it will be the attesting environment, which will have the key, this attestation key private part. For Intel, specifically the coding enclave, which will have access to this key. And that part will, so we have from the first project, we have not yet integrated the full artifacts into this. For this, we have taken a very simple approach to make it more generic, because Intel also intends to, via the trust authority, apply it for different TEs. So this is not specific to Intel. This is generically representation of the evidence, which is a user-defined data and a device status containing all the claims, and all of them are signed via the private key, which is with the attesting environment, and this one as the target environment.
Question: when you say all the claims, what does that refer to?
Sorry, say again. All the claims.
You said it contains all the claims, and I'm wondering, what does that refer to?
Okay, right. So this is containing the claims, which means the measurement of the target environment. For instance, for Intel, this will be MR enclave, MR signer, and everything which is a part of the code. Everything other than the user-defined data, which is in Intel's terminology, the R data. So everything else is a part of the device status.
So in a scenario where you have a root of trust and a dice layering scenario, that would include all of those measurements as well, like everything below the measurements of the TEE is included in dev status.
So I tried to have, and we also internally discussed about the dice layering. We couldn't find any proper explanation of how would this exactly map to the dice layering. So I don't have specifically. If you have any reference, then I would be happy to go through it, and we can, as co-authors, also discuss internally. If you can refer us to something which describes, of course, there is one paper by DICE, or one white paper on DICE. I think that's also formally verified by Microsoft. But the point is more like, how does the, let's say, Intel SGX or TDX or any TEE, how does it relate to this protocol implementation in DICE layering, for instance?
So if you think about the like an enclave or a TD, like the tenant level environment, that TEE is different from, for example, the quoting TD or the quoting enclave. And then all enclaves or TDs depend on the microarchitecture for trust. In other words, the instruction sets that implement the abstraction of an enclave or a TD is like the root of trust, if you will. And so that's a pretty simple but reasonable dice layering scenario. And so so the question is, when you say device status, is it just for the tenant TEE representation in evidence, or is it everything that the tenant TD or an enclave depends on? Is that intended to be included in whatever you're calling it, device status?
So one concrete question in my mind was, if what would be when we call it I think the terminology that DICE is using is the certificate, which is alias, I think is the terminology that it uses, which is the certificate which is generated on the fly. So my question here was, would it be TD code or would it be the PCK cert? which one of these exactly would it be?
Yeah, so PCK cert describes the root of trust environment. And then there's the rest of the, there's sort of the layering that gets you to the quoting TD, but then there's also the tenant TD, which is another layer on top.
So is it specified somewhere, like the way you were describing, like which layers?
I'm not aware. Well, I'm not aware of a public document that tries to relate, specifically dice layering to SGX or TDX.
Right.
But really dice layering is just saying there's trust dependency, like there's multiple modules in the endpoint and there's trust dependency between the modules. That's the main point. And whether you're using dice terminology or some other terminology, the concept is that there's trust dependency in the form of a graph, and this is showing a trust dependency graph here as well. And so the question is about what's the assumption about the trust dependency graph in the bit that you heard describing in terms of the status. Does it include the entire graph, or is it just one node in the graph?
So at the moment we have completely abstracted this, so it could be seen in any way. But I think is a good thing to maybe make it more precise if at some point of time that document becomes available, which is kind of describing the mapping you mentioned. So I was still thinking about how to kind of, is it using the same layering, or is it using some different layering for the dice implementation, and kind of try to relate it to so the problem also is not in this layering. This is only verifying the certificates back up to the root certificate authority, and problem from protocol perspective is how to map that dice kind of thing into a protocol structure, which is looking something like this. Would it be that maybe an interesting question to ask here would be whether this kind of protocol would be run for the one of the layers, or would it be run for each of the layers? So how do these, at the protocol level, can I precisely think about these layerings?
The way SPDM dealt with this is they treated all of the certificates, so they use the terminology alias intermediate certificate to refer to dynamically generated certificates for components that are dynamically instantiated, and that the SPDM endpoint could be on top of a layer cake of dynamically generated environments. So you could model the same thing with TLS, because TLS accepts the certificate chain, and in DICE and SPDM, it relies on the certificates to provide evidence for any of the layers that are beneath the layer that implements the SPDM endpoint. And so I think it's the same architecture for TLS as well. But in the case of SGX and TDX, it may or may not, use certificates that, they have proprietary, in essence, it's like a proprietary certificate format for some of the evidence that's produced. But you can think of it, if you think of it as a certificate that's dynamically generated, it kind of fits that model as well.
So this certificate will then be dynamically generated per handshake.
It could be. I don't know that it necessarily is. The point is it's dynamically generated from deployment, as opposed to something that's known at manufacturing time and is described by an EK certificate that's issued by the manufacturer.
Right. it would, just from the top of my head, I think it will reduce the problem because it's now deployment time, as you were mentioning, but the problem will still remain that if it is reused across the session, the problem is reusing across the session. And if it's still, I think it would still be possible to use it across the sessions because nothing is binding it to.
Yeah. So I think kind of where the direction that this talk seems to be heading is that you want anything that's dynamic to be fresh, and if freshness is determined by a nonce that's provided by the verifier, then you want that to cascade down all of the dynamic layers until you get to a static layer, which you would call the root of trust, and then redo all all of those dynamic things with the nonce so that you have freshness in all the layers that you depend on. I mean, that's kind of that would be the nirvana answer.
Right. Okay. Then yeah, this is just showing what I already explained. So in red are the changes to the standard TLS. Certificate is self-signed and signatures are done via the ephemeral key. And here there are steps for the verifier to proceed with the verification. And and one important thing is that we assume that this long-term key of the verifier is known to the client reliably. And this is a one-way authenticated channel. One way of representing this is what we have used here. And then it signs using its private key, which the client can then use its public key to verify the signatures and then also verify the proof of possession or these signatures. And then the finished messages are the same as before, as the standard TLS. Okay, then this part is about the properties. Finally, the way we try to formalize is that injective events in proverif, which means that we check whether the receiver can accept multiple evidences corresponding to a single sent evidence. In this case, from the server. The other way around, it will be symmetric or analogous. And then we have some cases that we have. I can quickly just show. I think it is, for example, the case without the verifier, in which there is only a server and a client. So two different instances of the client can actually accept the same evidence. And then we have some examples when there is one-way authenticated channel, the way I showed it, that the verifier or the client actually has the verifier public key, authentic public key, in which case, again, this verifier accepts two different sessions of the verifier can accept this single sent evidence from the server, this one. And even if the channel between the two is secure, it's still possible to replay, which means that the two different verifiers can then still accept the evidence, even if the channel between these client and the verifier are actually secure. So these three different scenarios we have.
Does that double verifier scenario assume that the verifiers cooperate in providing a freshness nonce?
Sorry, say again. So the verifier?
I thought there was two verifier scenario. Do the verifiers cooperate in sharing a freshness nonce, or are there two freshness?
So sorry. So this is not two different verifiers. These are the two different sessions of the same verifier.
Okay.
So in all the figures, it's representing, for example, when there is this client and client, it means different session of the same client. So what we are showing is that actually two different instances of, let's say maybe it's easier to discuss here. So two different instances of the client are able to accept the evidence while it was sent only for by the server for a specific, not specific, of course, it's not specific. That's why they can use it. It was sent only once, but it can be replayed across two different sessions of the client.
Hey, Osama, just a quick time check. We got about 5 minutes, so
Okay, so then I will
make sure you get the most value out of them, based on what you want feedback on or present. Thanks.
Yeah, sure. So I think I'm done. This is just a summary to the thing that maybe the most important things that we learned from this exercise was the formal model which existed from India, and it's around 6 years that has been used in many works. It was not commented. We had to look into the different key schedules and so on. So how does it work? And then we kind of recommend that comments are important not only in the piece of codes, but also in the formal models. And the validation of the formal models is also necessary. As I showed, there are at least two major problems in the key hierarchy of TLS implementation. And to date, we didn't find any works which have actually mentioned this as an issue, although it has been used in many works. Also, last year, the LERC proposal is also using the same artifacts, draft 20. Yeah, so we also recommend that to utilize the UFMRG offering of formal verification to keep the artifacts up to date for complex protocols and extensions of TLS, and the usability of formal tools. So the initial India model, when we tried to do this replay property, it took over a month in the high-end server to actually give some results. So that was also one thing, that the tools, and the only people who can actually solve this are the developers themselves. So it's not a very usable tool. So we really need to make these tools more usable. And quickly about the next plans, as I discussed last time. So we are trying to now formalize this, which is in the other thing, which is the intra handshake. And we are discussing the remaining issues, and the plan is then to go for the call for adoption for this draft. And we are compiling all the issues to be discussed at the UFMRG mailing list or the next meeting. And the final thing is about if anyone is interested in this work, or if someone at your organization has expertise, we would very much welcome the contributions or feedback on the work. Yeah, I think that's it. So
Cool. Thank you, Osama. Definitely very enlightening for me. So mechanics for the next meeting. We got a couple minutes left here. Jim, Keith. Is Keith here? No, it looks like, Keith is still here.
Yes. I can share the next one if that's what you're getting to.
Yeah, there's one person